Welcome to this video. Dear children, you read about division in previous classes. So today, in this video, let's see how division is related to Euclid's division lemma. We have 59 chocolates and 3 boxes. We have to keep equal number of chocolates in all the 3 boxes. Can you keep an equal number of chocolates in these boxes? Well done! We saw that 19 chocolates are kept in each box, whereas 2 chocolates remain. Just think, now can you solve it with simple division method? Absolutely right. On solving, we get quotient equals to 19 and remainder 2, where 3 is divisor and 59 is dividend. Now if you want to keep the same chocolates in 5 boxes instead of 3, such that there are equal number of chocolates in each box, then what will you do? Well done! Now we have 11 chocolates in each box, while 4 chocolates still remain, which we represent in this way. Similarly, if the number of boxes is increased to 7, we see that each box contains 8 chocolates, while 3 chocolates remain, which we represent like this. In the above 3 situations, we saw that both dividend and divisor are positive integers. Where on dividing the dividend 59 by divisor 3, 5, 7, we got 2, 4, and 3 respectively. On observing carefully, we get to know that in all the 3 situations, the remainder is less than the divisor, where we represent dividend by A, divisor by B, quotient by Q, and remainder by R. In the above situations, 2 positive integers A and B are seen, where A is greater than B. And there exists unique integers Q and R. On division, we get remainder R, which is greater than or equal to 0 and less than B, from which we can say that A is equal to B times Q plus R. This is known as Euclid's division lemma. Today in this video, we studied the Euclid's division lemma. In the next video, we will learn to find the HCF using this. Welcome to this video. In our previous video, we studied the Euclid's division lemma. Today, in this video, we will learn to find the HCF using Euclid's division lemma. The number of chocolates P and chocolate Q are 1215 and 891 respectively. What is the maximum number of chocolates that can be kept in a box, and how many minimum boxes are required to keep equal number of each chocolate? you can also solve this by hit and trial method. But here we will solve this in a stepwise manner, for which we will find the HCF, that is, highest common factor of the number of both types of chocolates. For this, we will use Euclid's division lemma A equals to B multiplied by Q plus R. Let's try to solve it together. Here, 1215 is greater than 891. Now we will use Euclid's division lemma on these, which gives us this value. Since the remainder is not equal to 0, we apply the Euclid's division lemma again to divisor 891 and remainder 324. And by this, we get this value. Here also, the remainder is not equal to 0, so we apply the Euclid's division lemma once again. The remainder has now become 0, so our procedure stops here. Since the divisor at this stage is 81, which is the HCF of 1215 and 891, so maximum 81 chocolates can be kept in the box out of chocolate P and chocolate Q. Since we have to find the minimum number of boxes required, can you tell what we have to do in order to find this? Well done! If we divide the number of chocolates P and chocolate Q by 81, that is, the maximum number of chocolates that can be kept in a box, and add the quotients obtained, we get 26, which is the minimum number of boxes required. Hence, minimum 26 boxes are required to keep the chocolates. Now, let's understand the difference between Euclid's division lemma and Euclid's division algorithm. Euclid's division lemma is a proven statement which is used to prove another statement, while algorithm is a series of well-defined steps which is used to find the HCF of two positive integers a and b, where we can use the statement a equals to b multiplied by q plus r of Euclid's division lemma. Today in this video, we saw an example based on Euclid's division lemma. In the next video, we will see the common errors which occur while solving these types of questions. Welcome to this video. In the previous video, we saw an example based on Euclid's division lemma. Now we will see the common errors which occur while solving these types of questions. Example 1. A shopkeeper has 1,517 pairs of shoes and 902 pairs of slippers. He wants to keep them in boxes in such a way that the number of pairs of each type of footwear remains equal. How many pairs can be put in each box to do this? Pause the video to solve the question and then match your answer. Since here we have to find out the equal number of pairs of both type of footwear that can be kept in the box, so we have to find out the HCF of both, and for this we use Euclid's division lemma. Here 1517 is greater than 902, So we substitute the value of a and b and solve. If you have selected option 1, then it's a good try. But it's a wrong answer. As while using Euclid's division lemma, you hastily select dividend in place of divisor, because of which your answer gets wrong. Here, to find HCF, we used Euclid's division algorithm, which is based on Euclid's division lemma. If you have chosen option 2, then it's a good try. But this is also a wrong answer, because when you apply Euclid's division lemma again to the new divisor 902 and 615, then you get negative remainder, which is not correct, as in the lemma. Value of r is not negative. It is either greater than or equal to 0. And in this procedure, we don't get 0 as the remainder value. This we also ignore. And for this reason, here, you consider 615 as the HCF of 1517 and 902. Hence, your answer becomes wrong. If you have chosen the third option, then it's correct. To find the HCF, let's solve this using Euclid's division lemma. Here, 1517 is greater than 902. We repeat the process of Euclid's division lemma until the remainder is 0. Here we get remainder 0. So the process ends here. Since the divisor at this stage is 41, so the HCF of 1517 and 902 is 41. So the option 3 is correct. Hope you must have understood why the third option in this example is correct and the rest all are incorrect. Teachers can also check the understanding of the students in the class with the help of such examples.
Hello everyone, welcome to this video. In our previous video, we learned about Euclid's division lemma. In this video, we will study the fundamental theorem of arithmetic. Can you group these numbers into composite numbers and prime numbers? Pause the video to group them and then match your answer. Hope your answer is correct. Now if we choose any one of these numbers, suppose 102 and proceed, then can you write 102 as the product of its prime factors? (102) can be written as the product of its prime factors, that is 2, 3 and 17. Well done! Now if we observe it carefully, then we will notice that we can multiply prime numbers to get a natural number. Let us understand this in detail. If we take a group of prime numbers, and multiply some or all these numbers any number of times, we will get a positive integer in each case. Therefore, we can say that any positive integer can be written as the product of powers of prime numbers. Can you think of any composite number which cannot be written as the product of powers of prime numbers? Let us try to answer this. Let us factorize a positive integer, say 1,08,108. Can you show how to factorize this number? Perfect. We can find its factors with the help of a factor tree. In this way, we can factorize 1,08,108 as a product of prime numbers, which is in the form of powers of prime numbers. What do you understand from this? From this we understand that every composite number can be written as the product of the powers of prime numbers. And if the sequence of prime numbers is not taken into consideration, then composite number can be written in the same method as the powers of the prime number. You can check this theorem by trying out some more examples of similar kind. This is a true statement which plays an important role in the study of integers. This is the reason why this statement is called the fundamental theorem of arithmetic. It was introduced by Sir Carl Friedrich Gauss.
According to him, each composite number can be expressed or factorized as a product of prime numbers, and this factorization is unique irrespective of the order of the prime factors.
In this video, we have studied the fundamental theorem of arithmetic. In the next video, we will see few of its applications. Hello everyone, welcome to this video. In the previous video, we learnt about the fundamental theorem of arithmetic. In this video, we will see few of its applications. Can you write 12 and 45 as the product of their prime factors? Pause the video to factorize it and try it yourself. Well done! If you have written the same prime factors, then your answer is correct. But if you have written some other factors, then your answer is wrong because the uniqueness of the fundamental theorem of arithmetic determines that each composite number can be expressed as a product of prime numbers, and this factorization is unique except for the order of the factors. Let us now discuss the factors of 12 and 45. We can see that the common factors of both the numbers is 3. What do you understand by this? We have learned in the previous video that the product of the common prime factors of two positive numbers is called the highest common factor, HCF. Also, if we observe carefully, like HCF, we can also find the least common multiple, LCM, which is the product of the highest powers of the prime factors of both the numbers, that is the LCM of 12 and 45 is 180. What more do you notice here? Can you guess what will we get if we multiply HCF and LCM of 12 and 45?
Perfect. We will get 540.
On observing carefully, we find that it is equal to the product of 12 and 45. On the basis of which, it can be concluded that the product of any two positive integers, a and b, and the product of their HCF and LCM are the same. Now the question arises whether the same rule is applicable if we take more than two numbers. Let's examine this with the help of two examples. We shall take the HCF and LCM of 3 numbers in the first case and 4 numbers in the second case. On solving, you will find that the product of numbers and the product of their HCF and LCM are not equal. Thus, we can say that this statement is not valid for more than two positive integers. You can also test this by taking any group of numbers yourself. In this video, we learnt about the relationship between two positive integers and their HCF and LCM with the help of the fundamental theorem of arithmetic. In the next video, we will see an example based on this. Hello everyone, welcome to this video. In the previous video, we learned about the fundamental theorem of arithmetic. In this video, we will see some interesting examples based on it. Check whether there is any value of n for which 7 raised to the power n ends with digit 0. We know that if a number ends with 0, it will be divisible by 10. So, we can say that if the number 7 raised to the power n ends with the digit 0, then it will be divisible by 10. This means that 7 raised to n should have 2 and 5 among its prime factors. Is it possible? No, this is not possible because if we look at the prime factorization of 7, we get only 1 and 7. So, the uniqueness of the fundamental theorem of arithmetic guarantees that there are no other primes, that is, 2 and 5, in the factorization of 7 raised to the power n. Based on this, we can say that there is no natural number which has the power of 7 raised to n whose last digit is 0. Let us look at another example. The HCF and LCM of two numbers a and b are 51 and 4,335 respectively. If A is equal to 255, find the value of B. Can you guess how the value of B can be found? We learned in our previous video that the product of two positive integers and the product of their HCF and LCM is always the same. Now, if we substitute these values given in the question in this formula and solve them, hence, the value of B will be 867. In this video, we have seen an example based on the fundamental theorem of arithmetic and observed the relationship between two positive integers and their HCF and LCM. Hopefully, you have understood the fundamental theorem of arithmetic and its use. Hello everyone and welcome to this video. In our previous video, we studied the fundamental theorem of arithmetic. Now, we will study theorems related to irrational numbers. You all know that real numbers are made up of rational and irrational numbers. Dear children, can you sort these real numbers into rational and irrational numbers? Well done! The numbers in the first column are rational because they can be written as P over Q. And the numbers in the second column are irrational because they cannot be written as P over Q. Let us consider an interesting fact. Let's divide the number 64 by 2. We get 32 as the answer. Can you guess the square root of 64? Absolutely right. It is 8. Is 8 divisible by 2? Yes. If 8 is divided by 2, we get 4 as the answer. If we continue to do the same with other numbers, what do you observe? Based on these examples, we can say that for a positive integer a, if the power of a is 2 and it is divisible by any prime number, say b, then the number a will also be divisible by b. Come on, let us consider the square root of 7, which is an irrational number. Suppose that the square root of 7 is a rational number. Therefore, we can obtain two integers a and b such that the square root is 7 is equal to a upon b and b is not equal to 0. Suppose a and b do not have any common factor other than 1, where a and b are co-prime. By squaring both sides and rearranging, we get 7b square is equal to a square. That means that 7 divides a square. Therefore, 7 will also divide a. Suppose, when we divide a by 7, we get c as a quotient, where c is an integer. Putting the value of a in equation 1 and solving, we get b square is equal to 7c square. This shows that 7 divides b square. Then 7 will also divide b. according to the given irrational number square root of 7, we get two results here. Thus, we know that A and B have at least one common factor and that the common factor is 7. Note that we had assumed that A and B do not have any common factors other than 1. Whereas the opposite or contradiction of this is obtained. This contradiction has occurred because we have made an incorrect or erroneous assumption that the square root of 7 is a rational number. Therefore, we have proven that the square root 7 is an irrational number because we found a common factor other than 1 in A and B. In this video, we studied theorems related to irrational numbers. In the next video, we will see examples related to this. We welcome you to this video. In our previous video, we had discussed theorems related to irrational numbers. Now, we will see an example based on this. Riddhi and Nidhi were discussing something between themselves in the class. When the teacher came and asked them, "What are you discussing?" Riddhi states that 5 plus square root 7 is a rational number, while Nidhi says that it is an irrational number. The teacher asks them to explain why 5 plus square root of 7 should be a rational number or why should it be an irrational number. Nidhi assumes that 5 plus square root of 7 is a rational number, which is written as P upon Q, where P and Q are integers. On rearranging equation 1, we get square root of 7 equals to P minus 5Q upon Q. Since you will remember that the difference of rational numbers is also a rational number, we can say that since P and Q are rational numbers, then P minus 5Q upon Q on the right side is also a rational number. But the square root of 7 on the left side is an irrational number. But this is impossible because irrational numbers cannot be equal to rational numbers. Hence, Nidhi tells Riddhi that 5 plus square root of 7 is a rational number is a wrong assumption because what we have obtained here is contradictory to it. Hence, we can say that 5 plus square root of 7 is an irrational number. In this video, we saw an example based on theorems related to irrational numbers. In the next video, we will see some common mistakes that are observed while solving these types of questions. Hello everyone and welcome to this video. In the previous video, we saw an interesting example based on theorems related to irrational numbers, which was quite interesting. In this video, we will see the common mistakes that are made while solving these types of questions. Which of the following statements is true for 3 square root 17? Pause the video to solve the question, solve it, and then match your answer. Let us first assume that 3 square root 17 is a rational number. So, we will write it as follows, where P and Q are co-prime numbers, and P and Q have no common factors other than 1. If we rearrange this, we will get square root of 17 is equal to P upon 3Q. You may remember that the division of rational numbers is also a rational number. Thus, we can say that since P and Q are rational numbers, then the value on the right side, which is P upon 3Q, is also a rational number. Therefore, the square root of 17 will also be a rational number. Can you write square root of 17 as P upon 3Q? No. The square root of 17 cannot be written as P over 3Q. That is, it is an irrational number. This contradiction was caused due to our misconception, because we considered the square root of 17 as a rational number. Therefore, 3 square root of 17 would also be an irrational number. Hence, option 2 is the correct answer. If you have chosen the first option, it is a good try. But this answer is wrong, because if you rearrange it, you will get square root of 17 equal to P upon 3Q. You have determined that on the right-hand side, P and Q are integers. So P over 3Q will be a rational number. Hence, on the left side, square root of 17 should also be rational. But you missed out the fact that square root of 17 is an irrational number and no irrational number can be equal to a rational number. Because of this, your answer is wrong. So hopefully, you must have understood why the second option is right in this example and why the first option is wrong. Teachers can also test the understanding of students in the class with the help of such examples. Hello everyone and welcome to this video. In our previous video, we have studied the theorem based on rational numbers and irrational numbers. Now we will discuss decimal expansion of rational numbers. Can you write the decimal expansion of these rational numbers? To practice this, pause the video to try and then check your answer. Can you tell which method have we used here? Perfect! We have used the division method here. What do you understand by looking at these decimal expansions? You studied in your last class that the decimal expansion of a rational number P upon Q, where Q is not 0, will either be terminating, like here. The decimal expansion of 33 upon 8 is terminating. Or non-terminating, that is repeating, like here, the decimal expansion of 2 upon 11 is repeated and non-terminating. Now, the question is, should we use the same method to find out whether the decimal expansion of a rational number is terminating or non-terminating? Or do we have some other method as well? Let's discuss these decimal numbers to find out. You can see that all these can be expressed as rational numbers in this manner, whose denominator is a power of 10. Now, if we write the numerator and denominator in the form of their prime factors, then we cancel out their common factors. Now, what do you see here? we can see here that all real numbers whose decimal expansion is terminating are written as a rational number in the form of P upon Q, where P and Q are co-prime. And the denominator, that is Q, has only powers of 2 or powers of 5 or powers of both 2 and 5. This is because the prime factors of 10 are only 2 and 5. So, the powers of 10 will remain in the form of powers of 2 and 5. Based on this, we can say that if x is a rational number whose decimal expansion is terminating, then x can be expressed as P upon Q, where P and Q are co-prime, and the prime factorization of Q is 2 raised to the power n into 5 raised to the power m, where n and m are non-negative integers. Now, if we look at these rational numbers, then can you guess whether their decimal expansion will be terminating or non-terminating? If we solve by division method, we understand that the decimal expansion of the first and second rational numbers is terminating, and the decimal expansion of the third and fourth rational numbers is non-terminating. If we take the numerator and denominator of these rational numbers in the form of prime factors, you will see that the denominator of terminating rational numbers can be written as 2 raised to n into 5 raised to m, while the denominator of non-terminating rational numbers cannot be written in this format. Thus, we can say that the inverse of the theorem we just studied is also true, which we can formally write as follows. Suppose x equals P upon Q is a rational number such that Q is in the form of 2 raised to n into 5 raised to m, where n and m are non-negative integers. Then, the decimal expansion of x will be terminating. And if Q is not in the form of 2 raised to n into 5 raised to m, then the decimal expansion of x will be a non-terminating rational number. In this video, we discussed the decimal expansion of rational numbers. In the next video, we will see examples based on it. Hello everyone and welcome to this video. In the last video, we discussed the decimal expansion of rational numbers. Now, we will see an example based on it. Here, without using division, we have to tell which rational numbers have a terminating decimal expansion and which ones have non-terminating decimal expansion. Can you guess how to find this out? Pause the video and try to solve this question. If we factorize both the numerator and denominator of this first rational number, we find that the denominator is in the form of 2 raised to n into 5 raised to m. In our previous video, we learned that in a rational number P upon Q, if Q is in the form of 2 raised to n into 5 raised to m, where n and m are non-negative integers, then the decimal expansion of the number is terminating. So, the decimal expansion of this number is also terminating. Let us now discuss the second rational number, 17 upon 15. After analyzing it, we see that the denominator is not in the form of 2 raised to n into 5 raised to m. You will remember that in a rational number p upon q, if q is not in the form of 2 raised to n into 5 raised to m, then the decimal expansion of the number is non-terminating. Similarly, we can also find out the decimal expansion of the remaining rational numbers. So, the decimal expansions of the first, fourth and fifth rational numbers will be terminating. And the decimal expansions of the second and third rational numbers will be infinitely recurring, that is, non-terminating. In this video, we saw examples based on decimal expansion of rational numbers. In the next video, we will see interesting examples based on real numbers. Hello everyone and welcome to this video. In the previous video, we saw some examples based on decimal expansions of rational numbers. In this video, we will see some interesting examples based on real numbers. So come on, let's discuss these real numbers. What can you tell about these numbers by looking at them? These are all real numbers, and real numbers are a set of rational and irrational numbers. So first, we look at these irrational numbers. Can you guess what their decimal expansions would be like? We know that the decimal expansion of all irrational numbers is non-terminating, non-repeating. Now, let's move to rational numbers. Moving forward, if we observe the decimal expansion of this number, we can see that these 3 points at the end of the number tell us that the decimal expansion is non-terminating, and the digits after the decimal 8, 3, 4, 5 and 6 are recurring. So, the decimal expansion of this real number will be non-terminating, repeating. We can also write this number in this way by putting a bar. What do you understand by this bar above the digits? This bar above the digits represents the group of digits that are recurring. Like in this number, the digits 2 and 7 are recurring. So, the decimal expansion of this rational number will be non-terminating, repeating. So, we can say that if a number has a digit or a group of digits with this bar above them, the decimal expansion of that number is non-terminating, repeating. Now, if we look at 29 upon 1000, we can write it straight as 0.029 based on the knowledge of our previous classes. Or, we can factorize the numerator and denominator as the denominator is in the form of 2 raised to n into 5 raised to m. Both ways lead to the same conclusion that the decimal expansion of this rational number will be terminating. Because we learned that in a rational number, p upon q, if q is in the form of 2 raised to n into 5 raised to m, the decimal expansion of such a rational number will be terminating. And if q is not in the form of 2 raised to n into 5 raised to m, the decimal expansion of such a rational number will be non-terminating, repeating. As you can see in this number. Now, find out the decimal expansion of this rational number using the rules that you have learned in this video. In this video, we discussed real numbers, rational numbers, and irrational numbers.